Hello, class. Um, this is going to be the video for section 5.3, rational functions. This is the last video that covers topics in Unit 3. The only thing left will be our test review. But this is a short unit in terms of number of sections, but there's a lot packed into each section. So, as always, I have, or almost always, I have lecture notes posted in Blackboard. That's what we'll be using as the base for our notes today. In addition, this is definitely one of those sections where being able to see what we're doing is very helpful. So I highly recommend that if you have if you're using a TI graphic calculator or any graphing calculator, or if not the Desmos graphing app, to go ahead and get those out, get signed into Desmos. And that's remember, it is something that you can use on the test as well. And the teacher and me, there's two sides to the technology. One is, theoretically, you should be able to do all of the stuff that we're doing without a calculator. It's just like arithmetic. You should be able to do all the fractions, all the integers, all the order of operations without calculators. You have a better understanding, right? So it would be far too easy for most of what we're doing in Unit 3 to be able to graph all these things we're doing and not have any understanding of the algebra and still you at least get a halfway decent exam score, like maybe not passing, but still there's a lot you can do just by able to look at these graphs. All right, so there's a hesitancy on one side of my math teaching mind to talk about the graphing part of it. On the other hand, so many of us are visual learners, and this is definitely one of those units, and this section in particular, where if you can see the graph side by side with what we're doing with the algebra, that is such a powerful learning tool. And I highly recommend that. Hopefully you're doing this throughout Unit 3, is that you're learning how to use either your TI or whatever graphic calculator you have, or Desmos graphing, to see that the algebra and the graph side by side. And a lot of times I think when students who learn how to use their graphing tools don't get to the test and don't really need it because you've got a better understanding of the concepts. All right, so this is particularly if you're a visual learner, I definitely recommend that you use your graphing calculator, use the Desmos graphing app, and I'm going to be using the Desmos graphing app quite a bit as we go through this content today. All right, so let's get into the content and see exactly what it is we're talking about, and then go from there. Okay, so for rational functions, so the generic rational function is of the form f of x equals p of x over q of x. And so what does that mean is now it's rational numbers or fractions. Now we're doing fractions with polynomials in the top and the bottom. Okay, so I'm not just dealing with fraction numbers, we're doing polynomial fractions. Okay? And then the other thing that we're always going to say is that q of x cannot be equal to 0. Why is q of x not equal to 0? Because we can't divide by 0 and get a real number answer. Now notice that does not say x not equal to 0. It says q of x cannot be equal to 0. Because there's going to be, the majority of the polynomials that we have here, we plug in x equals 0, then we're not going to get 0 in the bottom, we'll get some other number. Okay. That concept right there, where we cannot be equal to 0, is one of the core features of what we're going to be talking about with these rational functions. It has a huge impact on the graph. And that's actually the first thing we're going to get into once we start going there. All right. Remember, rational functions are just fractions that have polynomials top and bottom. Now, they could be really messy polynomials. I mean, you could have like an x to the fifth, and so on here. Most of the time, they're going to be either constants, particularly, on the top, we always have to have an x on the bottom. But they could be just like, it could be just x, could be x squared plus 3. And they're going to be relatively small polynomials, but they're still polynomials. Okay. So what do we need to be able to do with our rational functions and their graphs? Okay. By the time we're done, we're going to be able to identify the domain of any of these rational functions. If that's something we've been doing for a while now. Vertical asymptotes. which, by the way, vertical and horizontal asymptotes, I don't know, I think it's one of the funner words that we have in math. But P is silent. And I finally did my homework and looked up the origin of the word asymptote. It's actually Greek. All right. And it means, what does it mean? What's the official meaning of asymptote? It means not falling together. So, in short, asymptotes, this isn't the full math definition. Basically, asymptotes are lines that we get closer to as we're drawing the graph as we get to positive or negative infinity. And since we're going to be talking about vertical and horizontal asymptotes, there's going to be an up or down sort of approaching that line and a left or right approaching that line. And those two things together are going to be the main factor, or one of the main factors in how we graph these rational functions. So like with the parabolas, the quadratic functions, the x squared, we had the U shape, the vertex was like the key component of the graph. Well, for rational functions, it's where is the horizontal and vertical asymptotes. So that's what we're going to spend most of our time talking about. And then the other thing is, once sort of like in 5.1 where we had a lot of things separately to talk about, and then we put them together in 5.2. Same idea here in 5.3, except there's not a separate section. We're just going to do first part of 5.3 is kind of doing the individual pieces with the domain, asymptotes, and then we're going to put it all together in graphs, and we're also going to see our transformations. All right, so just in a nutshell, vertical asymptotes is a vertical line where these graphs are going to get closer and closer together, and so we're going to get like vertical parts of our graph. And then horizontal asymptotes, these are basically, I think of these as like the end behavior of the polynomial graphs. This is the equivalent of the end behavior. So the horizontal asymptotes control kind of like what happens to the far left and far right of the graph. All right, so in a nutshell, that's what we're going to be talking about today. Now, before we jump into the algebra of all that, let's look at the core rational functions. And so the first one is 1 over x. Good. And again, I apologize for the small graph. And so I'm going to bring up Desmos here in a second. The next one is going to be the 1 over x squared. Next, so this top one is 1 over x. And so this, my program flipped these. I was trying to get it formatted. Sorry about that. This is 1 over x squared. This is 1 over x. Trying to get these to fit in one column. It probably took me 10 minutes trying to get my program to work, and I just realized it's still backwards. All right. So the bottom graph, that is 1 over x. We called this the reciprocal function back when we did transformations and we had our library of functions, and then we didn't talk about it again. Well, now we're talking about it. And so the 1 over x, the basic 1 over x, has this nice little curve in quadrant 1, and then the same curve in quadrant 3. This is an odd function because if you flip it across both axes, it will lie on top of itself. Okay, now if you notice, and I'm going to bring this up in Desmos right quick so you can see a better picture. But right here in the middle, it splits. And so almost all of these rational functions are what we call discontinuous. You have to lift your pencil to draw, when you're drawing this, you have to lift your pencil and then go to this. All right, and so there's, where does that split occur? Well, it occurs right on the y-axis, which is where x equals 0. And why is x equals 0 important? Well, what happens when you plug in 0 into 1 over x? You get a divide by 0. So it's not a coincidence that this graph splits right there at x equals 0 because of our graph. That's going to be key in what we're doing the rest of the video. And so when we do our asymptotes, all asymptotes they're not actually, they're not points on the line, but they're important features that help shape it. And so we do in dashed lines. And so we have a vertical asymptote, which is just going to be VA at x equals 0. So the core vertical asymptote for the basic function is at x equals 0. And with vertical asymptotes, we're going to, as we get closer and closer to 0, on the on the 1 over x, as we get closer and closer to 0 from the negative side, so like negative 0.1, negative 0.001, and so on, you're going down to negative infinity. Because you have 1 over a really small negative number, which gives you a really large, when you do the division, it gives you a really large negative number. And so it's not vertical, but it gets steep really quick. It is going down to negative infinity. If you look on the other side, when x is positive, you're getting closer and closer to 0, like 0.1, 0.001. 1 divided by that gives you a really large positive number. So at these vertical asymptotes, our graphs are going to be going either up or down to positive infinity. So that's the vertical asymptote. Almost all rational functions have vertical asymptotes. There are exceptions, and we'll do one, maybe two examples of those. But in general, almost all rational functions have these vertical asymptotes. Now, if you notice as we go to the left and the right, they start to get kind of flat, but again, they're not horizontal. They're just they're getting close to flat. And if you notice, what are they getting close to? Right there at y equals 0, the x-axis. So that is a horizontal asymptote, which is going to be HA at y equals 0. Right. So all rational functions will have some sort of asymptote. In 2/3 of the cases, it'll be a horizontal asymptote, and another one it'll be what we call a oblique or a slant asymptote. We're not going to deal too much with those, but I'll show you what they look like. We're mainly going to be dealing with horizontal asymptotes. It doesn't have to be at 0; it could be moved up or down. But this is like the core rational function we're talking about today. So let's go into Desmos right quick, just to give you a little bit better picture. Oh, and when you're doing these on your calculator or in Desmos, these are fractions. And so make sure, let's see, Desmos doesn't have a fraction button. The one thing you have to be careful of is make sure that you put these in properly. And notice I got a fraction bar right there. How I did that was the backward slash, which is right next to the shift button on the calculator. If you do that, you get a fraction. And if you do that first, you get a fraction. And I highly recommend that you do that, or on the graphing calculators, use your fraction button. Is if you don't, and you just do divided by and start using parentheses, it's very easy once they start getting a little complicated to input them wrong. And I'll show you examples of that later. Okay, so here is our 1 over x. So it's a nice little curve. Now, as I zoom out, it looks like it's horizontal. As we go to the far left and far right, it is not horizontal. It is, if you zoom in, it is slightly increasing, but it's just getting really, really close to 0. Now, the horizontal asymptotes, you can cross them occasionally, like wherever the vertical asymptotes are. Sometimes, like we might see something that comes up above it and then comes back down. So it is occasionally possible to cross the horizontal asymptote. The vertical asymptote, you can never cross it. You have to lift your pencil and go over to the other side. Because like I said, if they're there, they're going to be going to positive and negative infinity. Let me see if I know I can do y equals 0. Do dash lines. I'm sure there's a way in Desmos to do dash lines. I don't know how to do it. Can they do? All right. So yeah, so I don't know how well you can see. It's not necessarily bright blue, but there is y equals 0. So there's the horizontal asymptote. And so you can see they look like they merge, but that's just because physically, these lines are so close to each other. If I zoom in, you can see there is a small difference. But if you do 1 over 10, that's 0.1. If you do 1 over 20, that's 0.05 or 0.02. But you're getting closer and closer to 0 if you're doing 1 divided by a number that's getting larger and larger. So that is the horizontal asymptote. Now the green is the vertical asymptote. And so that is x equals 0. So if you notice, again, as we go down to negative infinity, we're getting close, or as we get closer and closer to 0 from the left side, we're going down to negative infinity. And again, it may look like it's vertical, but again, we're not actually touching that line. Okay, so in MyMathLab, they actually, I think I picked all the problems that don't have you actually have to use the tools to graph this. I'm pretty sure in MyMathLab they're all matching. But one thing you want to do, anytime you're looking for graphs of horizontal of rational functions, find out where the horizontal and vertical asymptotes are. Yeah, most of the time we'll ask them ahead of time, but even if we don't, you still want to find out where they are, because that's sort of where the graph is centered. So just to show you, let me do a transformation in here. So we're looking ahead a little bit. And so remember, horizontal transformations are inside with the x, vertical are outside. And so inside on a rational function is down in the denominator. Okay, and so what does -2 do? Well, horizontal stuff is backwards, so it actually moves it right 2. And if you notice, that vertical asymptote is now over at 2. So we basically shifted this entire graph to the right 2, which also shifts the vertical asymptote. How do we do a vertical shift up or down? Well, we add something outside the function. So let's say that I add 4 outside the fraction part. Now, if you notice, it went up 4, and so the horizontal asymptote is now at 4. So when we get into transformations, we're taking that graph that's at 0, 0. Instead of tracking a vertex like we did with the parabola, I'm going to track where is that horizontal and vertical asymptote, like where's the center of those. And so this moved right 2 up 4. So we moved right 2 with vertical asymptote, up 4 with the horizontal asymptote. Okay, so that's why I've said that the asymptotes are sort of like the key feature of these graphs. All right, so back to what I had. So 1 over x is the basic rational function, and it has horizontal and vertical asymptotes at y equals 0. If you look on the paper at the top one, that is 1 over x squared. So let me show you what that looks like, which is basically it's going to be the same graph. Let me do another one. Oh, I did this with backward slash after I did the one, and it still gave me a fraction bar. So that's good. All right, let me turn these off for a second. All right, so I don't know how well it's coming through here, but the red is the 1 over x. The black is 1 over x squared. So let me turn that off. So there is our 1 over x squared. So really it's the 1 over x, but when you square a negative value, that what we had in the third quadrant, that flips it up and makes it positive values. And it's a little bit steeper than 1 over x because, if you square a number, it's going to be bigger than not squaring. So 1 over x is like this. And now as we graph these, sometimes they're going to be, there might be more pieces this. Like if it goes up or down to positive, negative, infinity, you really kind of have to like plug in points and see what's happening with the numbers. But they're always going to be split, and they're always going to be these nice little curves. They can get more complicated, like if I did. And so now this one has 3 pieces. It's got that nice little curve on the left, nice little curve on the right, and then kind of a flat parabola in the middle. All right, so there's a reason for that that we'll get to shortly, but they can get more complicated than just those like 2 nice little curves. but this is all our rational functions are going to look somewhat, along these lines. Okay, so that's kind of a quick overview of what the graphs look like. And now let's talk about the algebra behind why the graphs are the way they are. So for that, let me go back to the notes. All right, okay. So before we talk specifically on the horizontal vertical asymptotes, we talk about domain. And so domain of a function is all, it's the x's, and more specifically, it's the x's that we can plug in to get an answer. Okay. And so think of it this way, domain is going to be all real numbers equals all real numbers except where x makes divide by 0. So we don't want x values that make us divide by 0. Those are not going to be in the domain. Everything else is good. So the way we're going to do this, and I'll do this on a separate sheet of paper, is step 1. If you're looking for the domain, set the denominator equal to 0 and solve. So those are what makes us divide by 0. And we don't care about the numerator because we can have 0 on top. 0 divided by number is 0. It's the denominator that gets us the error. And then step 2, the domain equals, so it's going to be, again, from negative infinity to positive infinity, except where x equals the answer to number 1. So if we found out in step 1 that x is equal to 4, then that means the domain is going to be all real numbers except x equals 4. Okay. Or if we found that we get 3 and negative 7, that's where it makes us divide by 0, then the domain's going to be all real numbers except 3 and negative 7. Okay. And we're going to put that in interval notation, which can be a little messy, but I think it's that's the most efficient way to say it in terms of math. So let's get off to the side here and just jump into some problems. All right, so number 2, h of x is x plus 9 over x squared minus 25, and our goal is find the domain. Okay. So what x's can we plug into this function and get a valid output? All right, so step 1, set the denominator equal to 0 and solve. Okay, so how are you going to solve that? Well, the preferred way would be to do it by factoring, because this is a difference of squares. So that's just x plus 5, x minus 5 equal to 0. And so we just set each of those equal to 0. We get x equals 5, we get x equals negative 5. Or some of you are going to probably do the square root property. So you're going to add 25 to both sides. And now how do you solve for x? It's square to both sides. And some of you are going to remember why I don't like this, because what do many of you forget? You got to do plus or minus. We're going to do square root property, you got to do plus or minus. So you get x equals 5 plus or minus 5. Okay. All right. If you forget the plus or minus, you're just getting half the answer. Okay. All right. So what does those x represent? Those x represent where we divide by 0. Okay. Now, depending on who coded the problem in MyMathLab, they may just say x equals and then put an answer box and say the domain. I really wish they wouldn't do that. I think most of the time they're good about putting the domain in interval form. remember, domain is going to be all real numbers except plus or negative 5. So let's do this visually. Anytime we're doing interval notation. Okay, so if we're saying we don't want 5 and negative 5, that means on a number line, we would put an open circle on both of those. All right, and so but it's going to be everything else except negative 5 and 5. Okay. And the reason I like doing this on the number line is now you can see we've got 3 intervals. So we got the left, the middle, and the right. So what's the interval for the left one? Negative infinity to negative 5. And now this is where I see them use union. We'll look at the homework in the end. They might say commas, but this is another place where union is normally used because it means or. So it could be this space or. Don't forget the middle one. Lots of students will do the left and the right and forget the middle. So we do have from negative 5 to 5. Now, remember, we're using parentheses because we can't equal negative 5 or 5. If we equal them, that would be a closed circle, and then that would make us divide by 0 up here. And then we have another one, interval, so do union, and then 5 to infinity. That is the best way to put the domain. Depending on, I've seen problems where they said x is not equal to, and then you would do negative 5 and 5, which it really makes you focus on the two things it's not, because we can't plug in 5 or negative 5, but any other number you plug in here will work other than those two. Okay, we're going to do a couple more of these, and then I'm going to bring up on Desmos graphing so you can see exactly what we're talking about here. How about the next one, number 3? So f of x equals x plus 8 over x squared minus 4x. Again, we want the domain. Okay. And so we don't care about the top because we can have 0 divided by number, so just take the bottom, set it equal to 0, and solve. All right. So how do you factor that? Okay, well, if you get stuck, it is a quadratic, so you could put it in the quadratic formula where a is 1, b is negative 4, c is 0 because there's no constant. And then the answer that you'll get in the quadratic formula will be your x equals. So that's what it'll bypass all the factoring if you get stuck on that. Okay, or there's a GCF of x. So factoring that out. And so that tells us x equals 0, x minus 4 equals 0. So we get x equals 0, and that gives us plus 4. Okay, so there is where we divide by 0. Shouldn't have circled that because that's not our answer. Because our answer is, what is the domain? So we don't want 0 and positive 4. So we have open circle on 0 and 4, everything else in between. So that is negative infinity to 0, union 0 to 4, union 4 to infinity. Now we're not always going to have 3 intervals. Like if there was just one number where we divide by 0, then you would basically just have 2 intervals. So, but it's fairly common to have 2 numbers that don't work, and so we're going to have 3 intervals in the answer. Okay, so there is our domain. All right, so before we do the next one, let's put this in our graphing app, either in Desmos or your TI, whichever graphing calculator you use. All right, so we have x plus 9 over x squared minus 25. Okay. So I showed you one of these earlier. So since we have 2 notice we have three pieces. So we've got a left, a right, and a middle. Now, where do they go vertical? Sometimes it's hard to tell, but in this case, it's pretty clear that's at -5 and at 5, that's where we go vertical with our graph. Why are we going vertical with the graph? What did we say our domain was on number 2? It was all real numbers except -5 and 5. Okay. So when we do vertical asymptotes, we're doing the same exact process. It's just we want the numbers, not the x asymptote is where we divide by 0. Domain is everything else. So when I think of domain and vertical asymptotes, I think of two sides of a different the two sides of a coin. Right. So they're both where we divide by 0. It's just, do we want all the rest of the numbers, or do we want those numbers specifically where we get our vertical asymptotes? Okay, so that is number 2. And then we'll graph number 3. So we have x plus 8 over x squared minus 4x. All right, let me turn this over off. All right, so again, we get the funky kind of shape. And so where does it go vertical? Sometimes you got to like zoom in and zoom out to really kind of get a good picture. But right there at x equals 0, it's got a vertical line. And then at x equals 4 is our other vertical line. And so what did we say the domain was? The domain was all real numbers except 0 and 4. Now, it's not always going to look like, I don't know, like a volcano on a downward parabola. Like if I come over here and put a negative, oh, not a negative there. I want a negative out front. So if I put a negative out front, what kind of transformation is that? Well, it's outside the function, so it's vertical now. And so what do you do when you do a negative? You flip it. Notice that it went from the outsides were up, and the middle was a downward parabola. And now it's exactly flipped. Okay, so if you put a negative out front of your fraction, you get a vertical flip. Take that vertical flip away, then it flips it back the other way. All right. So we're asking for the domain. So domain on this one is all real numbers except 0 and 4. Okay. And so if you get stuck on the factoring part, if you understand the graph and know how to put in your graphing calculator, your app, that can also help you answer the question. All right. What about number 4? So number 4, we have h of x is x plus 7 over x squared plus 64. And so anytime I'm talking domain, and in my brain, I'm always linking domain and vertical asymptote automatically, because like I said, once you find domain, you know the vertical asymptote, vice versa. All right, so how do we find domain? How do we find vertical asymptotes? Take the bottom, set equals 0, solve for x. Okay. Now this one doesn't factor because it's a sum of squares, not a difference of squares. Let's go ahead and use the square root property. Get x squared equals -64. Take the square root of both sides. Don't forget your plus or minus. And so what is the square root of -64? But in your calculator, it's giving you an error. Why are you getting an error? Because of that negative. Because remember, we can't take square root of a negative number, get a real answer. So there's always going to be an I involved. And so what's the square root of 64? It's 8. With plus or minus 8i. All right, so what does that mean about the domain? Well, while you're pondering that, I'm going to put this in Desmos. And again, like I said, I'm really like the visual aspects of this topic. All right. Wow, that looks where I'm zooming now looks like a flat line. If I zoom in really close, you can kind of see that it's got a bit of a hump to it. But you zoom out, it almost looks like a flat line. Right? And so if I go left, if I go right, there is no vertical like split on this graph. Okay. So what's happening? Well, to answer that, so looks like there is no vertical asymptote. Because if it did, it would have to happen by in like 64. So if I go out to, yeah, so no around negative 64 all the way here, positive 64, there are definitely no vertical parts in this graph. Okay. So what does it mean when we set the denominator equals 0 and got plus or minus 8i? Well, those are imaginary numbers. What is the domain? Domain is real numbers. Okay. So since we know, so there are no real numbers that when you plug it in that will ever get 0 in the bottom because you're taking 64 and you're adding it to something that you're squaring. If you're squaring a real number, it's always going to be 0 or positive. So that denominator will never equal 0. So the domain on this one is all real numbers, which is negative infinity to positive infinity. Okay, so this is, remember, I briefly mentioned that not every single rational function has a vertical asymptote. This is the example of one that does not. So if you don't divide by 0 with a real number, you don't get a vertical asymptote because the domain is all real numbers. All right, I'm still sure. Yeah, let me see if I can de-emphasize the flatness a little bit. So I've said +1 instead of plus 64. And so when I first drew it, it jumped up, so you're like, oh, maybe it's vertical, but no. You're going to get, some sort of parabolish shape, like a bell curve. If you've taken that statistics. And then so like if you make that number bigger or smaller, then like the bell curve gets flatter and it gets flat really quick. Okay. But there still is no vertical component because no matter what you plug in, you will never get divided by 0. All right. So that is how you, not only do you find domain by setting the denominator equals 0 and solving, it's also how you get the vertical asymptote. Okay. All right. Let's go ahead and back to the notes. Now, this note is a little bit out of order compared to the homework, but let's go ahead and, since it's here on number 5, let's go ahead and do that now, as we are talking a little bit about domain. This gets towards the end of the homework in 5.3 when they start like throwing it all together when they give you the graphs, but it doesn't hurt to talk about it now. All right, so find the domain and range of that graph. All right, so this has, let's see if I can see this here. We got a built-in magnifying glass. All right, so this has a horizontal asymptote at y equals 3, negative 3, as a vertical asymptote at x equals negative 2. Yeah, so that's where that vertical line is. It's x equals negative 2. That horizontal line is at y equals negative 3. Okay, why is that important? Well, for domain is all our x's, except where we divide by 0, and wherever we divide by 0 is where our vertical asymptotes are. So our domain, it's going to be all real numbers except x equals negative 2. So how do we put that in interval notation? Well, domain is left to right, so start on the left, negative infinity. Goes up to negative 2, put a parentheses, because we can't equal negative 2, that's why we have the vertical asymptote. and then union or possibly comma in MyMathLab. And then starts over at -2, goes to positive infinity because it goes forever to the right. So we're saying our domain is every number except -2 where we have that vertical asymptote. Now, what about the range? Now, sometimes the range can get a little bit trickier. If we cross that horizontal asymptote, which the most common time we cross that horizontal asymptote is like when we had those that had 3 pieces. Sometimes that parabola, that's the one that's most likely to cross the horizontal asymptote. But on here, neither of these cross the horizontal asymptote. It doesn't dip down and come back up. This one doesn't go above it and come back down. So this one's always above the horizontal asymptote. This piece is always below it. So what that means is there's no piece of the graph that ever equals -3 for y. Okay, so that means we have a gap. And so we have to do with our range just like we did with our domain. We need 2 pieces. All right, so remember range is low to high. So how low does the graph go? It goes negative, starts at -infinity. Then that piece goes up, doesn't ever quite get to -3, it just approaches it. So we need a parentheses on -3. And then we have another piece, we do union or possibly comma. And then low to high for this piece, it starts at -3 and then goes up forever. So our range is everything except y equals -3. To show you what I mean by like how it might cross, let me show you, like if I had a graph. Let's say that I had let's see. All right, so let's say that I have a horizontal asymptote at 2. Doesn't matter where the vertical asymptote is, but let's say I have something that looks like this. So these pieces here are never going to cross y equals 2. So without the middle piece, the range would be from -infinity to +2 and then 2 to infinity. But this piece here actually, does cross y equals 2. So there is no gap in the y value because the gap at the horizontal asymptote is covered by this piece. But if there's any place you have a vertical asymptote, there's always going to be a gap in your domain. 100%. Okay. So we'll talk more about that towards the end of this when we start putting it all together. All right. The vertical asymptote is the vertical line where, again, your function values, your y values are going to plus or minus infinity as your x approaches that vertical line from either side. So where do vertical asymptotes occur? Where we divide by 0. All right. So I feel like, let's see. Oh, in the notes, there is talks about the whole or removable discontinuity. I don't think this is currently in the homework. If it is, I'll back up and do it. That was in the old book, they talked about that. Basically, sometimes when you're factoring, like on this one, just, x squared minus 4 factors to x plus 2, x minus 2. And notice there is an x plus 2 in top, and you could cancel those out. If we had that case, there would be a hole at, that would be, when you saw that for 0, that would, saw that for x, that'd be -2. There'd be like a hole in the graph. And so for those who go on calculus, you might need to know that. But like I said, I'm pretty sure in this homework, we cut that part of it out. But we'll check the homework as we get to it. All right. Like I said, I feel like we've done these already. But let's do one more. All right, let's do number 8. X minus 9 over x squared minus 10x plus 24. And so now we're not looking for the domain, we're looking for the vertical asymptotes, if any. Okay. And why does it say if any? Because if we don't divide by 0, then we don't have a vertical asymptote. So like if you jump down here number 9, you're going to get an imaginary number there because we're doing 7 plus a number. That's never going to be 0. So that one will have no vertical asymptotes. But let's go back to this one. All right. So how do we find vertical asymptotes? So just like the domain, set your denominator equals 0 and solve. Okay. All right. And I'm going to go through the factoring kind of quick here, but remember, if you can't factor it, you do have the backup as the quadratic formula. And the answers you get from the quadratic formula should be the same answers we get from factoring. This one's going to, that's a plus, that tells us the signs are the same, that tells us the both are negative. So what multiplies to give us 24, and it's going to add to give us 10, 6 and 4. That gives you minus 6x minus 4x. That gives you plus 24. So I'm going through that kind of fast, but we're focusing on the other part of this. So set each of those equal to 0. Get x equals 6, x equals 4. And so this, if this is domain, it'd be all numbers except those two, but this is the vertical asymptotes. And these are vertical lines. So you need the x equals. We don't need just the number, we need the x equals. Otherwise, they're not vertical lines. So what if you get stuck on the factoring and the quadratic formula? And let's say you don't remember it. This is one reason I recommend having your graphing calculator or your app as a backup. I hope you're using that during the process to learn that, and to have that as a tool. Well, and like I said, doing the backslash on there automatically makes the fraction. Let me see if I can do it wrong. So x minus 9. Sure, properly, yeah. X minus 9 over x minus 6. X minus 4. Helpful to type in x minus 6 minus 4. Okay, so notice now, something weird is happening. See that slanted line? We don't have a horizontal line. That's what we call a oblique or slant asymptote. Okay. And when you look at the intercepts, well, looks like 4 and 6. So that may look weird, but you may think you have the right graph. That is not the right graph. And the reason being is when I did this over here, I didn't do the fraction bar until after the 9. So notice that's x is not in the numerator. But now I want to make sure it's up in the numerator. Now I get a horizontal asymptote. We're not always going to get a horizontal asymptote, but this one was supposed to have one. So now it's a little bit easier to see that yes, to the left of 5 and the right of 5 is where our vertical asymptotes are. That's the x equals 4, x equals 6. So if you got lost on the factory of the quadratic formula, and now notice I put it in factor form, I could have put in x squared minus 10x minus 24, got the same answer. Okay, so if you understand, what x-intercept or vertical asymptotes are, then if you can get the graph, then you can go in and find them. That's, that's getting closer and closer to 4, closer and closer to 6. Okay. All right. Is there anything else on vertical asymptotes? I think it covers everything. Like I said, we could do more vertical asymptote examples, but I think we did this when we were doing domain. That's why I kind of want to do this all together. Okay. So domain and vertical asymptotes, the way you find them, set the denominator equal to 0 and solve. And then domain is all real numbers except what it made you divide by 0. Vertical asymptotes are the vertical lines at those x's. All right. So that is kind of half the graph is where's the vertical asymptotes. Now let's talk about the horizontal asymptotes. Okay. And like I said, to me, comparing this to the polynomials, like the vertical asymptotes, like where those occur, that's sort of like knowing where the x-intercepts were for the polynomial graphs. And then now that we're doing the horizontal asymptotes, that is like the end behavior, what happens to the far left and to the far right of the graph. So let's go back to the notes. I'm on page 3 of the notes. Okay, so horizontal asymptotes is the horizontal line where the graph crosses as x goes to positive, negative, infinity. Okay, and we can occasionally cross those particularly close to the x, the vertical asymptotes, but not usually. But since they're horizontal lines, it's always of the form y equals a number. Okay. Now there are 3 cases. Okay. And so, there's not algebra to do on this. It's just basically comparing the degree of the top with the degree of the bottom. Like on this one, number 13, degree of the top is 1, degree of the bottom is 2. On 14, degree of the top is 3, degree of the bottom is 2. On 15, degree of the top is 1, degree of the bottom, denominator is 3. And the reason that we care about the degrees is we're taking x to positive and negative infinity. That's what we're looking at on the graphs. And so when you're taking x to positive or negative infinity, like the number that's going to control all this is the one that gives you the degree. Okay. So when you're going to positive negative infinity, x cubed is infinity cubed is bigger than infinity squared, right? So that's why we're only looking at the degree term for the numerator and denominator. That's really going to control kind of what the shape of the graph is. Okay. And so if you think of it that way, and like the number really isn't even important as you go to infinity. So like when you're looking at 13, the degree of the top is 1, the degree of the bottom is 2. So you're really acting like 1 x squared over x. And what is x squared divided by x? It's 1 over x. And then what happens when you plug in a really large number into 1, 1 divided by a really large number, that's approximately 0. Same if you plug in a really large negative number, 1 divided by a really large negative number, like 1 divided by negative 1,000,000, that's going to be close to 0. It's going to be slightly negative, but still going to be very close to 0. All right, so that's one of our cases is the first case. If the degree of the numerator is the degree of the numerator is p of x is the one in top, and then is less than the degree of the denominator, q of x, then the horizontal asymptote is at y equals 0. That's the case 1. That's what we've been dealing with so far. So the degree of the top is 1, degree of the bottom is 2, degree of the top is smaller. So the horizontal asymptote is at y equal 0. That's case 1. If the degrees are equal, so if it's degree 1 over 1, 2 over 2, 3 over 3, then we need to divide the leading coefficients. And the horizontal asymptote is at y equals that number. And so for example, if I gave you f of x is 3x to the 4th over negative 7x to the 4th. And so if you ignore the numbers, x 4th divided by x 4th is just 1. So this is really acting like 3 over negative 7. Those basically kind of cancel each other out. Because I mean, it could be more than that, but as you go to infinity, those are the important, right? So then your horizontal asymptote on this one would be y equals -3/7. That's if the degrees are equal. Okay, so case one, the degree of the top is smaller than the degree of the bottom. Horizontal asymptote is always at y equals 0. If the degrees are equal, then you divide the leading coefficients, and then your horizontal asymptote is at y equals whatever that number is. So like over here, that would have been at y equals -3/7. The third case is the degree of the numerator is larger than the denominator. If that's the case, there is no horizontal asymptote. This is what we call an oblique or a slant asymptote. So remember when I popped it up on the graph, then we had that slanted line. And so that's if the degree of the top is larger. So for example, if you have degree of the top is x cubed, degree of the bottom is x squared, that's going to act like x over 1 or just x. So you get y equals x. So y equals x, that's a line with a slope of 1. So that's where we're getting those. Or the oblique is the mathy term, the slant is the more descriptive term. But basically what's happening is instead of following a horizontal line like it does in the other two cases, it's going to follow a line that has a positive or negative slope. Okay. And I'll bring these up to show you, but that's case 3. Now, to find the actual line it approaches, that requires long division with polynomials, which is something that this semester we've cut out because we have to do so much review material in chapter 1 or unit 1 and unit 2 that we had to cut out some of this college algebra stuff. And so this semester I've decided we're not doing long division, which if you knew all that entails, you probably wouldn't complain. So well, all we're going to do is if it's case 3, where the degree of the numerator is larger than the degree of the bottom, then we're just going to say there is no horizontal asymptote. Okay. You don't actually have to find it. You just have to know that it's not horizontal, that it is slanted. Okay. So let me show you this, example of this in Desmos. All right, so this is still that one before where we have the x squared minus 9 or x minus 9 over x squared. And so if you look at this one, what is the degree of the top? Degree of top is 1. Degree of the denominator is 2. So the top degree is smaller. Anytime the degree of the top is smaller, horizontal asymptote is at y equals 0. So if you look at that, where does it go flat? As you go to positive negative infinity, it's at y equals 0, right there on the x-axis. But let's make this x squared, or not, let's make this x squared. If we make it x squared, now the degrees are the same. Okay, and so then you look at the coefficients. Well, that's 1x squared divided by 1x squared, which is 1. And so now it is, if you do a horizontal line, it's kind of, let me draw in that horizontal line. So there's y equals 1. And so notice it did cross the horizontal axis, but as we go to negative infinity, the red line, which is our graph, is getting closer and closer to the horizontal line of y equals 1. Same thing over here. As we go to y equals 1, as x goes to positive, we're getting closer and closer to that line. Like I said, so sometimes we can cross the horizontal asymptote near our vertical asymptotes. So that's when the degrees are the same. Now let's make this x cubed on the top. Okay. So now the degree of the top is 3, the degree of the bottom is 1. So notice we're not following a horizontal line. I'll put in y equals x. If I put in y equals x, notice that's what those lines are following as we go to positive and negative infinity. Now it's not always just y equals x. It could be any, y equals mx plus b. To know that's what requires the long division. I'm just doing really basic examples here, but if we had this case, then your answer would be, when we ask you where's the horizontal asymptote, you would say there is none. Okay, because The degree of the top is larger than the degree of the bottom, so there's no horizontal asymptote, it's a slant asymptote instead. Okay, so that's how you find horizontal asymptotes, is compare the degree of the top to the degree of the bottom and know what the three cases mean. Failing that, what's your backup? Being able to look at the graph and see where it is. Let's go back to the notes. Okay, so let's look at the examples. All right, so number 12, we have 12x squared over 3x squared plus 1. So what case are we in? Case 1, 2, or 3? Well, the degrees are equal. You have degree 2 and degree 2. So if they're equal, that's case 2. So now we're doing the leading coefficients. So y is equal to 12 over 3. If that's a fraction, you have to reduce. So it's y equals 4. And this is a horizontal line, so we need the y equals. So if the degrees are the same, divide the leading coefficients to get your y equals, get your horizontal asymptotes. So for number 13, what case are we in now? Well, the degree of the top is 1. The degree of the denominator is 2. So the degree of the top is smaller. So when the degree of the top is smaller, it's always at y equals 0. What about 14? The degree of the top is 3. Degree of the denominator is 2. So now the degree of the top is larger. So if the degree of the top is larger, there's no horizontal asymptote, because it's a slanted asymptote. But the answer will be no horizontal. And that will be a choice in MyMathLab. All right, so go ahead and do the next two right quick, and then we'll start putting this all together. What did you get for 15? Well, the degree of the top is 1, degree of the denominator is 3, so the degree of the top is smaller. So therefore, horizontal asymptote is always at y equals 0. Okay. So on 16, they're both degree 2. So the degrees are equal. Then you look at the leading coefficient of each of those. So that's a -4 over 1 or -4. All right. So those are the individual pieces. Now, before we do all those together, I want to also start talking about transformations. And so for transformations, we're still, we've been doing this for a couple tests now, or a couple sections. So if you're down there in the denominator, that is your horizontal. So if you're out here, or in the front or the back, that's when you do vertical. Run out of room. But you get, so if you're not in the fraction is horizontal, outside the fraction is vertical. And don't forget that all the horizontal stuff is backwards. So if you want to move it right, you would have to do minus a number. If you want to do left, you have to do plus a number. If you want to move it up or down, vertical works as normal. And so if you want to move something up, you would either do say you want to move it up 3, you'd either say 3 plus your fraction or your fraction plus 3. Doesn't matter, like front or back. You have to add it. If you want to do flips, and so if you do a negative outside the fraction, that would be a vertical flip. So that would be up and down. If you do a negative inside, that would be a horizontal flip, left to right. All right, so let's, and then again, in MyMathLab, these are all going to be matching. But let's do one, let's do a couple of these without matching. And then that'll make it, if you do it without matching, you're ahead of the game. Sometimes it's easier without the matching, I think, but you'll see what I mean once we get into MathLab. Okay. All right. So we're transforming 1 over x to 1 over x minus 5. So the question is, what does that minus 5 do to the graph? Well, it's in the fraction, so it's a horizontal. Horizontal is backwards, so minus 5 is going to move it right 5. So here's my question. What is moving right 5? Well, right and left moves your vertical asymptote. What's going to happen over here at 5, now our vertical asymptote is going to be moved over to 5. Now, what else do we know about the graph? Well, that's the vertical asymptote. Where's the horizontal asymptote? Horizontal asymptote, what's the degree of a constant? Well, that's 0. So 0 over 1. So the degree of the bottom is larger. So it's at y equals 0. So moving left or right does not move your horizontal asymptote. You have to move up or down to move your vertical asymptote. Sorry, your horizontal. So now you know, like, this is sort of like the center of the graph. And now what you have, if you want to be more specific, basically what I do is I plug in like 1x on either side of the asymptote. So I want to do x equals 4, do this at t. And then x equals 6. So I go 1 to the left, 1 to the right. And so often in matching, what you need to do is they're similar, and so you need like a point. And so that's what I do on the matching is same thing. I go to one side or the other, and then find the first point, see if it works, and go from there. If I plug in 4 here, well, 1 over 4 minus 5 is 1 over -1. So that's -1. So here's what I do is we're at 4 and -1. So 4, -1. Okay. So there's a point on that graph. Now, how do I graph that? Your asymptotes are what you approach. So do your nice little curve there, your nice little curve there. You don't need any more exact because that one point pretty much tells you, where you're at. And then if you do, say, +6, well, 6 minus 5 is 1. So 1 over 1. 1. So now I do 6, 1. That's going to be right there. So if that's that point, and those are my coordinate of my asymptotes. So that's the nice thing about the asymptotes is once you got a point on that graph, then you can kind of just fill it in. All right. Let's do a couple more of these. All right. So what does that +3 do to the graph? Well, it's with the fraction. And so that's going to be horizontal. The +3 moves it backwards, left 3. What does the +2 do? Well, up or down, so that's vertically up 2. So what's that going to do? That is going to tell us that the vertical asymptote moved left 3, so it's going to be x equals -3. If we move up 2, that's going to impact the horizontal asymptote. So started at 0, it's now up to 2. So now you can, a lot of times, especially with the matching, if you got your right asymptotes, that at least gets you a 50-50 shot. And then you put in like 1 point. And so like I would go in like x equals -4, -5, and give me 1 more point. Okay. So once these are matching, I think you'll get a little bit more of it. But identifying them is the important part. What does that -1 do to the graph? So that moves it right 1. Now I just noticed that negative, well, first of all, the 2, that's a shrink or stretch. So that looks like it's in the fraction, but when I said outside the fraction, I really should have said like adding, subtracting, because this is really the same as -2 times 1 over x minus 1. because that's negative 2 over 1 and multiply top and top. So when you have that in the numerator for a flip, that's a that's going to be a vertical part as well. So really to be horizontal has to be in the denominator of the fraction. Because that is up there, that's not with the x, down here is with the x. Okay, so that negative 2 is a vertical flip. And so like the 2, that's just a shrink or stretch. You don't really need to worry about that. You just need to know the negative is a vertical flip. Okay. And if you're not for sure, like if I have confusion now, since that negative 2 is with the fraction, what's your backup? Your graphing. Okay, so let's clear this. Okay. So now we want to do my fraction bar. We got negative 2 on top, and then x minus 1 in the denominator. Yeah. Now it's kind of hard to see, but let me zoom in because I was zoomed way out in the first time. So now you got the nice. Now normally, let me draw 1 over x. All right, so normally 1 over x. So first of all, we said it was what? We shifted right 1. And then so, as you zoom out, it's at 1 where it's vertical. And normally 1 over x is in quadrant 1 and quadrant 3. But that vertical flip, this right side is now flipped down. This left side is now flipped up. Okay. If you want to know what the 2 does, like if I make that just a negative, no, I need to keep that there. All right, so the purple, the outside one, is the negative 2. The black is just negative 1, so that negative 2 makes it a little bit narrower. It's really kind of hard to see with these because they get so vertical, but if you zoom in, like if I made this, say, negative 10, that's going to, widen it out. So what we really worried about is the fact that don't worry about the 2 itself unless it was added or subtracted. If it was out here and it was subtracted, so now it took that graph and moved the horizontal down too. So when you're dealing with transformations, this is the basic curve we're transforming. That's 1 over x. Okay, and so moving it left or right, when it's down here in the denominator, we'll move your vertical asymptote left or right. So look for where your vertical asymptote is. Moving it up or down, we'll move your horizontal asymptote. So try to find out where your horizontal asymptote is. And then I don't know if we ever flip these horizontally because but we could put a negative down here in the denominator. So, but the problem is, let me do that. So turn this off. So there is a vertical flip. Okay, so there's red is 1 over x. If we vertically flip it, take this side, flip it down, take this side, flip it up. But let's see what happens when I flip it horizontally. Notice it doesn't look like there's a new curve. I take the vertical flip away. The vertical and horizontal flip of 1 over x looks exactly the same because of the symmetry. All right, so that's why we're really probably not going to deal with horizontal flips left and right. We're going to stick with vertical flips up and down because when you get into more interesting curves or with more asymptotes, then you can you can see the flipping better. Particularly if there's like 3 pieces, but when you're doing transformations, so remember your core that you're transforming is 1 over x. Does the vertical asymptote move left or right? Does the horizontal asymptote move up or down? And are you flipping it? All right. Yeah, and we're going to get into MyMathLab so you can see all the graphs. Let's see. Oh, the one other thing before I get into MyMathLab is that they're going to ask is for the intercepts. Okay. Let's do the intercepts on a couple of these, and then we'll get into MyMathLab and do their graphing. Okay. So I'm going back to the notes. So 21 is f of x equals 2 over x plus 5. All right. Let's Now they're going to ask you for vertical and horizontal asymptotes. We've covered those, so I'm going to wait on that till we get into MyMathLab. But let's talk about x-intercept and y-intercept. These are not new topics, but the algebra dealing with them is, or it's a little bit more advanced. Okay, so how do we find any x-intercept? Again, y equals 0, or f of x equals 0. So it would be 0 equals 2 over x plus 5, and now I solve. Good. So how do we solve that equation? Okay. Well, this is one of the reasons we did all those equations, fractions, and the proportions. Back in Unit 1. You can either multiply this by the LCD, if you want to think of that as a fraction. So the LCD is x plus 5. Or it might be quicker to think of this as put that over 1 and do a cross product. Kind of doing the same math in the end. But I think this one's a little bit easier to explain. So we're doing x plus 5 times 0 equals 1 times 2. Well, 0 times anything is 0. We're getting 0 equals 2. So what does that tell us about the x-intercept? Well, there is no x in here. So this is false. So that means there is no x-intercept. Okay. And so the reason that we got no x-intercept is the numerator was a number. There was no x. So to get an x-intercept, actually what you're doing, because basically that we basically ignore the denominator because we're going to multiply it times 0. So for the x-intercept, what you do is you set the numerator equal to 0. So, because like I said, the denominator kind of cancels itself out. And so you're just left with whatever's on top equal to 0. So we'll do that with 22 as well and show you a different one. But if there is no x on top in the numerator, there is no x-intercept. Okay, so now how do you find y-intercepts? Well, again, x equals 0. Which is usually going to be the nicer version of this. So we get y equals 2 over 0 plus 5, which is 2/5. There's your y-intercept. That's where this graph crosses the y-axis. Okay. And if you're a little iffy on that, what do? Graph it. Okay. So we're graphing 2 over x plus 5. All right. So as expected, when we get -5 for x, that's going to divide by 0. So right there at -5, that's where our vertical asymptote is. Degree of the top is 0, degree of the bottom is 1. So degree of top is smaller, so y equals 0, so horizontal. Okay. Where does this cross the x-axis? It does not, because a horizontal asymptote is the x-axis, and we're not we're not crossing it here, we're just getting closer to it. So there is no x-intercept because it doesn't cross the x-axis. Where does it cross the y-axis? Well, that says 0.4. Well, guess what 2/5 is? There's your 0.4. All right, so just a refresher. So basically for the x-intercept, because of the way the math works, you're just setting the numerator equal to 0 and solving. There is no x on top, there is no x-intercept. For the y-intercept, just plug in x equals 0, do the arithmetic. So let's do 22. 22 is, it's got an x on top, so that'll help us with the x-intercept. So f of x is negative 2x over x minus 4. So the x-intercept, so x-intercept is plug in y equals 0 for f of x. We get 0 over negative 2x over x minus 4, which you can either multiply everything by the LCD, which is negative x minus 4, or the equivalent is make that a fraction over 1 and do your cross product. So the cross product is 0 times x minus 4 equals 1 times negative 2x. And so 0 times x minus 4 is just 0. 1 times negative 2x is negative 2x. So now do you see why I say you basically just set the denominator equal to 0? Sorry, the numerator. So for x-intercepts, set the numerator equal to 0. X equals 0. That is the x-intercept. How do we do y-intercept? Plug in x equals 0. Get y equals negative 2 times 0 over 0 minus 4, which is 0 over negative 4, which is 0. Which makes sense. Because if we plugged in y equals 0, got x equals 0, then if we plug in x equals 0, we should get y equals 0. So let's block this one. All right, so we have top negative 2x. The bottom, we've got x minus 4. All right. Let me zoom out. All right, so again, just to check, didn't ask for the asymptotes, but we divide by 4 when we divide by 0 when x equals 4. And so there's where the vertical part is at x equals 4. The numerator of the top is degree 1, numerator of the bottom is degree 1. So that means the horizontal asymptote is at the coefficients. So negative 2 divided by 1 is at negative 2. So if you look at these horizontal, it's at y equals negative 2. Oh, and that's the nice thing about this is like if you're guessing, type in the horizontal, like y equals, and then you can see, like if I typed in x equals, what do we say, x equals 4, then bam, there's our there's our vertical asymptote. But the real question here was where's the intercepts? Well, this one crosses the x and y axis right there at the origin, right there at 0, 0. And if you zoom out, it doesn't cross it anywhere else because it's like this side is getting closer and closer to negative 2. So it never gets up to 0. This side is also getting closer and closer to negative 2. It's already crossed, so it's not going to cross again. So 0, 0 is both the horizontal and vertical asymptote, or the x and y asymptote. Okay. So that is kind of the individual pieces. Let's get into MyMathLab, do some of the basics, and then see how they put it all together. Sharing already. Yeah. All right. So this is 5.3. Yeah, so there's what, 20 questions. Like I said, I think about the first 15 or so are kind of one-part questions, and then they get into the multi-step ones. Um, so like the first 15 or so, that's equivalent of section 5.1. We're kind of doing it piece by piece. And then the last few are like the 5.2 where it's all together. All right. Start you off nice and small. What is the graph of 1 over x? Well, that, yeah, hopefully by now you know that that's a, because that's like a vertical horizontal flip of 1 over x. C is that's our 1 over x squared, and then D would be the vertical flip of 1 over x squared. So you got to know what the basic 1 over x looks like. True or false? Decide whether the following statement is true or false. The graph of a rational function may intersect a vertical asymptote. Okay. You can never touch a vertical asymptote. You might touch a horizontal one, but never a vertical. So that is definitely false because at the vertical asymptote, we divide by 0. So you can't have your graph dividing by 0. That is illogical. All right. How do you find the domain? Same way you find the vertical asymptote is the domain, set the denominator equals 0, solve for x. The domain is going to be everything except that. So if we do -9, that's when we divide by 0. And so how do they want the answer? Write it in interval notation. And so this is where if it helps, go in the number line. And I would, since x equals -9, we don't want x equals -9. So put an open circle on -9. So the domain is going to be from negative infinity up to -9 with the parentheses. Yeah, let me put a comma right quick just to see if they'll accept the comma. I'm thinking they want the union, but they may have been nice. And so we stop at -9, and the next one starts at -9, goes to infinity. Do they accept it? All right, so what's wrong here is I put the comma. Okay. Now, one reason that I was it didn't say separate them by commas like it did when we're doing like the increasing and decreasing intervals. But if you notice down here in the button palette, they've got the U for the union. So make sure when you're doing your intervals in 5.3 that you're using the union. On the test, if you put a comma between them, I will give you full credit because that's how they did it in the last section. But unfortunately, like I said, they're not consistent in how they approach this. So that's the domain. Now they want the vertical asymptotes. Well, the vertical asymptotes, how do you find vertical asymptotes? Well, you take the bottom, set equals 0, and solve. And then wherever you get those vertical lines are your vertical asymptotes. So again, it's the opposite of domain. So in this one, if we divide by, if we get x equals 3 or -4, that's where we divide by 0. So we will have x equals 3 and x equals -4. Okay. And I even picked some multiple choice on this, so you don't have to worry about whether or not to write the x equals or not. But they are vertical lines. That's why we need it. All right, so that's the difference between domain questions, which is going to be all real numbers except where you divide by 0. So you need the interval notation versus vertical asymptote, where you're still dividing by 0, but now those values are your vertical asymptotes. And now we're going to horizontal. Okay, and notice I also put y equals in there. All right, so there's I chose some multiple choice in here to kind of help you transition, to make sure you slow down and reading the instructions. So for horizontal asymptote, remember that's where you're comparing the degree of the top and the bottom. So degree of the top is 1, degree of the bottom is 1, so they're equal. So if they're equal, you look at the coefficients. So 6 over 1 is 6, so it's y equals 6. Okay, this one, degree of the top is 2, degree of the bottom is 1, so the degree of the top is larger. So if the degree of the top is larger, what do we do? Well, if the degree of the top is larger, there's no horizontal asymptote. That gives us one of those slant or obliques. And again, remember, when in doubt, go in and plot it and see what you get. You would definitely, on number 11, you would definitely see, a slanted line. That'd be, I'm at y equals x again. All right, so there are some that are just, what's the vertical, what's the horizontal, just piece by piece. Okay, now they're starting to put together a little bit more. Now they want vertical and horizontal. Now, when I say horizontal and oblique, it's either they have horizontal, and then it's either at y equals 0 or y equals the coefficients, or there's no horizontal and then there is an oblique. Okay, so remember, for horizontal and oblique, it's either one or the other, not both. Okay. So for the vertical, let's see. So find the vertical. So that's where we divide by 0. So this would be -8. Okay. Now here are your choices. 1 vertical asymptote, 2 vertical asymptotes, or none. All right. So that none is when we get like an I in the bottom. But at -8, so there's only one. Now notice when it says 2, it has leftmost and rightmost. So make sure you're putting in order from left to right if there are 2. Like if there were 2 factors in the bottom, then we would need 2 there. So why did it count it wrong? Well, notice let me check the answer again. So notice that before, when it's multiple choice, the x equals there, I did not put the x equals. So this is one place where they're being picky, and I'm glad they are, because if you have a vertical asymptote, it's a vertical line. You need x equals. Probably gonna be a lot of people miss that. And remember, if you miss it and you don't know why, you're like, I know it's -8. Why are you telling me it's wrong? Don't forget to look at the example. Sometimes you got to scroll through. And so like the only real 0 is at -9. And so the vertical asymptote is at x equals -9. So you need that x equals. In the multiple choice, the x equals was there. So you didn't have to worry about it, but it's an important part of it. All right, horizontal asymptote. Okay, so let's compare the degrees. Degree of the top is 1, degree of the bottom is 1. And so that's when we look at the coefficients. It's 5/1, so it's y equals 5. Don't ever pick B for 2 horizontal asymptotes. There's never going to be 2 horizontal asymptotes. It's either 1 or none. And we said it's a degree, it's at y equals 5. And don't forget the y equals, because it is a horizontal line. So don't just put 5, because we need to know that it's y equals, not x equals. And then find the oblique asymptote. Well, if there's a horizontal asymptote, then there is no oblique. Okay. It's either this is the horizontal, or and I don't. It says type the equation. I'm pretty sure I made sure to pick these that don't have an oblique, because we haven't done the division. All right, so vertical asymptotes. Ooh, this is with those of you for doing the video. You're going to get a little bonus. I probably shouldn't have put this one in here because of the factoring, but it's actually a little bit messy on the factoring. I would not do this on the test. All right, so for the vertical asymptote, set the denominator equal to 0 and solve. Okay, so here's the fun part on this one. That's not x squared anymore, so we can't use the quadratic formula. Okay, so what do? Well, factoring wise, this is a difference of squares, because what squared is this? Something squared minus something squared. Well, how do you get x to the 4th? It's x squared times x squared. How do you get 81? It's 9 times 9. So this is a difference of squares. So it goes to x squared minus 9, x squared plus 9. Okay. Now, have we solved for x yet? No, because we got to set each of these equal to 0. Now we solve these. So if I add 9 to both sides, we could factor it, but let's practice our square root property. Don't forget your plus or minus. So we get x equals plus or minus 3. Over here, x squared equals -9. Take the square root. Don't forget your plus or minus. So x squared, or x equals plus or minus. What's the square root of -9? That is 3i. Can we graph 3i? No. We get x equals 3, x equals -3. And we need x equals on both of them because they're vertical lines. Now let me put this in MyMathLab and then show you how else you can get the answer if that factoring. If we didn't do a lot like this, right, but this to me is when you stretch your muscle type questions. All right, so let's put this in MyMathLab and then show you how else to get the answer. All right, so it now has 2 vertical asymptotes. Now notice either 1 or 2 or none, so there is no option for 4. Right? So the leftmost is x equals -3. Again, don't forget the x equals. This is a vertical line. Right one is x equals 3. All right, let's say the algebra on this one really messed you up and you didn't know how to get started. How do you get the vertical asymptote? All right, this is why I've been pushing the graph. So what do we have? We have x squared on top. And on the bottom, we have x to the 4th minus 81. All right, so we're looking for vertical asymptotes. So there are 2 spots where this graph splits. And if you're not for sure if there's more, zoom out. There's definitely not anymore. Like once I hit 81, I don't need to zoom out past 81. I can go to 100, -100. Those are the only 2 spots there's vertical looking lines. And where do those vertical lines happen? Right, so it's halfway between -2 and -4. So there's our x equals -3. Halfway between 2 and 4. So there's our x equals 3. And when in doubt, type in x equals 3. Bam, there you can see exactly where it's at. Okay, same with x equals -3. Right there, now you can see for sure that that's where your vertical lines are. On the TI, I don't think you can put vertical lines in on the graphing calculators. You do that with the app. All right, so if, again, in 5.3, if the algebra is throwing you, don't forget you can look at the graph. All right, okay, so the next question was the horizontal asymptote. Am I sharing at the right screen? Yeah. All right, so compare the degrees. Degree of the top is 2, degree of the bottom is 4, so the degree of the top is smaller. Anytime the degree of the top is smaller, y equals 0. And again, since there is a horizontal, there is no oblique. Okay. And again, don't forget you can look at the graph. And you can see that there's our horizontal asymptote at y equals 0. And again, when in doubt, type in y equals 0. And then it might be hard to see, but there's a green line right there. That's definitely our horizontal asymptote. Okay. All right. So that is like a partial multi-step question. It's just what's the horizontal and vertical. And like I said, it's going to ask for oblique, but the examples I'm giving you are not going to have an oblique because we didn't do the algebra to do that. All right. So here's the multi-step questions, main and range. And so they give you the picture. So let's look at this a little bigger. All right. There is, okay, so the domain is left to right. And so remember, if you have a vertical asymptote, there's going to be a gap in the domain. The gap in the domain is at your vertical asymptote. All right. Now this one's a bit annoying. Is that counting by ones or twos? 1, 2, 3, 4, 5, 6, 7. This is counting by ones. And so where is the vertical? It's at x equals -4. So that's what I would do first before I do anything else on this, is it has a vertical asymptote at x equals -4. Sorry, +4. Where's the horizontal asymptote? Well, the horizontal asymptote is like they're counting by ones again, so it looks like 1. And I thought, I thought they would do a better job of letting you like see the graphs, but all right. Okay. So just like with the parabola, you like always do the vertex first, and then everything comes from the vertex. When you get to the end here and you're doing these graphs with everything, find your horizontal vertical asymptote first. Everything else kind of goes from there. So now when we do the domain, well, it's going to start. Domain is left to right. There's a split right here at 4. So the left side is going to start at -infinity and go to 4. And then again, put parentheses on domain and range here because we can't equal 4. And then it says interval notation, doesn't say anything about a comma between them. So make sure you use the U for the union. And don't use the U on the keyboard. I think that will count it wrong. Let me check. And then the right interval starts at 4 on the left, goes to +infinity. Let me see if it likes the. Okay, so it doesn't even like the U for the letter U. So you got to make sure you use the union button on the keyboard. Now for the range is low to high. And so the one thing you have to ask yourself is there a gap at the horizontal asymptote? Does this left side ever go above, like cross the horizontal side? Does the right side ever cross it? No. So there's a gap right there at y equals 1. So go low to high for the bottom. So the low is -infinity. Where does it go up to? The horizontal asymptote of y equals 1. And then parentheses, because we can't equal, union button, parentheses. And so for all of these, where one interval stops, the next one, takes over. So we're basically saying everything except 1. Okay, so now find the intercepts. Now notice it does not say x-intercept and y-intercept separately. Okay, so and we don't have a function to plug anything in, so this is just looking at the graph. So where does this graph cross the x-axis and y-axis? What happens, you kind of have to assume that happen. What does that look like? It looks like 0, 0. So they're not trying to trick you. And that's the only one, right? Doesn't cross the y-axis anywhere else, doesn't cross the x-axis anywhere else. So that's going to be a common intercept. Okay, so now what do they want? They want the horizontal asymptotes. It's kind of weird they asked the horizontal first, but horizontal asymptote, well, we've already figured that out. There's 1 at y equal 1. Don't forget the y equals. And then they want the vertical asymptote, which we already found that at x equals 4, and there's only one of them. There's only one split in the graph. Now remember, if there's a horizontal, there is no oblique. Okay. So you're going to have a couple like that. Okay, they're going to give you the graph. And again, before you do anything else, find the horizontal and vertical asymptote. Because when you find the horizontal and vertical asymptote, those will affect your domain and your range. Now notice on the intercepts, like here, they actually give you the 0.04. So they made that a little bit easier. right, so that's one way that you have all of this together. Okay, then we also have transformations. All right, so 6 plus 1 over x. So what does that 6 do? Well, anytime we're subtracting, it's a shift. It's not in the fraction, so it's a vertical shift. Vertical is a plus 6, so that's going to go up 6. Okay. To move left or right, it would have to be down here in the denominator. And so, we often think of that like 1 over x plus 6, the 6 at the end. But sometimes with these rational ones, they put the vertical up or down in front. So just watch out for that. That would, and something else to be careful of. If that was -6 plus that would be down 6. But if it was 6 minus that would be up 6 and a vertical flip. So if there's a negative in there, make sure see if the negative is just on the fraction or just on the number. Okay, so now we have to choose the graph. Now we just said that graph moved up 6. Okay, so remember the 1 over x, the horizontal vertical starts at 0, 0. And then if we moved up 6, track that. Well, that one looks up 6. That one's left 6, so it's not that one. That one's right 6, so it's not C. D is down 6. So A is the only one that got moved up. So track that. Where is that horizontal and vertical asymptote at? Okay, the domain. Well, the domain is all real numbers except where we divide by 0. Okay, and so if you notice, it's right still here in the middle. And now we have a function. So where do you divide by 0 with 1 over x? When x is 0. Oh, see, I just did the vertical asymptote. Domain's the opposite of that. So we want everything except 0. Then we're getting towards the end of the video. I'm getting tired, just kind of like you are with some of these longer homework assignments. So if I get in a hurry, I make mistakes just like y'all can. So it's everything except 0. So negative infinity to 0, and then union button, and then 0 to infinity. Again, when in doubt, don't forget, look at the example. And if you ever, if you're still not figuring out why you're missing it, don't forget about the Ask My Instructor. Sometimes it's its own button. Sometimes you have to get more help. But if you got an answer in there and you ask my instructor, a lot of times I can work backwards and help you out. Okay, so what about the range? Range is low to high. And so it's again the real question you have to ask yourself, is the horizontal asymptote a gap or not? Well, yes, because it doesn't actually cross the horizontal asymptote, so it's everything except where is it? We moved to up 6, it's everything except 6. So from negative infinity 6. Union. That's why, again, that's why I say when you're doing these graphs all together, before you do anything else, before you answer their questions, find your horizontal and vertical asymptotes. Because since that horizontal asymptote was at 6, that's why I know 6 is not in the range. And since the vertical asymptote was at x equals 0, I knew 0 was not in the domain. Now, this is where for vertical asymptote, that's my x equals 0 that I tried to answer earlier. The horizontal asymptote was at y6. But do you kind of see what I mean by like if you do those first, it kind of like helps out the whole problem. And then there is no oblique because there was a horizontal. So that is what the last 3 questions are like. Like on this one, that negative is up there with the fraction, but it's not in the denominator. So remember that negative up there will be a vertical flip. Okay, so normally it was in quadrants 1 and 3. So now it's going to be flipped. So it's either A or C. So how do you know if it's A or C? Because those have both been vertically flipped. Well, now you need to know where is the vertical asymptote. It's at 1. That's where we divide by 0. So if you look at it, there's your vertical asymptote at x equals 1. This one has a vertical asymptote at -1. So it can't be C. So just from the vertical asymptote, it either had to be A or D. Because D also had a, at 1 vertical asymptote. But that negative meant it was a flip. And honestly, whether you think it was horizontal or vertical flip, it still looks the same. Because you take that in quadrant 1, flip it down, get that. Or if you take it in quadrant 1, flip it this way, then you get this. Okay, so either way, that negative in front of 3 makes it a reflection. And then you go through and do all the other stuff. All right, so that is rational functions. Yep. So for rational functions, make sure you know that for both the main and vertical asymptote, that's where you divide by 0. The only difference is the main is all real numbers except where you divided by 0. The vertical asymptotes are the numbers where you divide by 0. And then the horizontal asymptote, you have to be able to compare the degree of the top with the degree of the bottom, and then know the 3 cases. Because if the degree of the top is smaller, horizontal asymptotes at y equals 0. If the degrees are equal, then you have to do the leading coefficients. And then if the degree of the top is larger, there's no horizontal asymptote, it's an oblique or a slant. And then I'll leave it up to you on whether or not you want to use your Desmos app or your graphic calculator to give you backup, but I would highly recommend it. All right, that is all I have for this video. Next video coming up will be the test review. All right, have a good day.